Surveying large areas in near-infrared light, a single image from WFIRST will have all the depth and sharpness to which Hubble has accustomed us, but will cover 100 times the area. In fact, a single image will encompass as many as 1 million galaxies. The new telescope's work will slip into the groove already made by Kepler, the Sloan Digital Survey, and TESS, the Transit Exoplanet Survey satellite. WFIRST will use microlensing rather than the transit method of detection. It will employ a 2.4-meter diameter telescope provided by the National Reconnaissance Office. But the best of both worlds part of the WFIRST story comes with the coronagraph, which NASA has been able to add to its instrumental array. This is a means of dimming the light from a so-called host star in order to see better the planet or planets orbiting it. And that is highly significant if we remember that the host star may be up to 1 billion times brighter than any exoplanet identified. If successful, the coronagraph technique will make it much easier to determine the chemical composition of planetary atmospheres. WFIRST will be able to use a unique deformable telescope controlled by computer. This first mission, due for launch in the mid-2020s, being what is called a technology demonstration, laying down a scientific marker for future missions to go in even more determined pursuit of life beyond the confines of our own solar system. While all of this is going on in space, here on Earth, another agency will be tackling the question of dark matter from yet another angle. At CERN in Geneva, the Large Hadron Collider is now running at full power for the first time.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphoton. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV, and what is most important, that these particles could be searched for at low energy experiment, with fixed target experiment.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
So the idea is that when the high-energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high-energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
Might its scientists be able to replicate dark matter itself?